Okay, today we're looking at binomial expansions in the form a plus b raised to the n. So when we talk about n, understand that n is simply our power of this binomial. So suppose we want to expand x plus 4 squared and simplify. Well, x plus 4 squared is the same as x plus 4 times x plus 4, which if we were to expand this out using FOIL, we'd have x squared plus 4x plus 16. And if we were to combine our like terms, we would end up with 3 total terms. We'd have x squared plus 8x plus 16. Okay? Now notice that there are 3 total terms in this expansion. And notice how the power, or the n value that we started with, was 2. This suggests that if we're talking about a plus b to the n, there are n plus 1 total terms. And that will always be the case. Now I want to talk about what is happening to the powers of a, and then what is happening to the powers of b. Recall that a is our first term in the binomial, and with our example, it's corresponding to the x. Well, if we look at the x values, notice it's starting with a power of 2, which is n, and then it appears to be going down by 1. This x in the middle here is really to the first power, and on the end, even though we don't see it written, there's really an x to the 0, which is just 1. So what's happening to the powers of a is that it is going to start at n and go down by 1. Now the powers of b. b is the second term in our binomial, and in our example it was the 4. Now this is a little bit harder to see, and it's actually going to be the opposite of what we just said here. Instead of starting at n and going up by 1, this is actually going to start at 0 and go up by 1. So what we really have here is 4 to the 0, 4 to the first, and 4 squared. Well, we can see that 4 squared is 16, but there's some confusion here in how do we get 8x from the 4. Well, notice we had a couple 4x's to combine, so that 4 got multiplied by 2. So that's where that 8 comes from. And our x squared, well, 4 to the 0 is just 1, so that really isn't showing up. Okay, so the powers of our second term, b, start at 0 and will increase by 1 until you hit your n value. So now we're going to take a look at situations where we're looking to expand a binomial and we have a power greater than 2. And we're not going to look to do it algebraically like we did before. So suppose we're looking to expand x plus 2 cubed using Pascal's triangle and your knowledge of what's happening to the powers of each term. That's what we just talked about up above. Now let's review Pascal's triangle. Okay. First of all, understand that this is going to give us the coefficients of the terms in the expansion. So let's write that down. Gives the coefficients of the terms in the expansion. And now let's construct it. There's a 1 on the top, 1, 1. Recall from last year, if you were to just add the 2 above, you're going to get your new numbers. So we simply are adding to get our triangle. Okay, so understand where this triangle is coming from. And I want you to connect it back to this a plus b raised to the n. Now, in our first row here, n is really 0. I want you to understand why. If I were to plug 0 into what we have up above, we would have a plus b to the 0, which is just 1. Okay? Which confirms the 1 we see right there. Suppose n were 1. Well, a plus b, if n is 1, well, that would just give us a plus b in our expansion, and notice that the coefficients of each of these is 1. That's why we see the 1 and the 1. And our next row, n is 2, so that suggests we would have a plus b squared, which if we were to multiply this out, we'd have a squared plus 2ab plus b squared. So notice the coefficients are 1, 2, and 1, which is what we see here. 1, 2, and 1. So there's the 1, there's the 2, and there's really a 1 there. Okay? So each of these rows correspond to n values. And notice that the total number of terms is always 1 more than the n value. So with our last example here, where n is 5, notice that there are 6 total terms in this row. Okay? So now let's look to expand our example, x plus 2 cubed. So from this example, our n value is 3, which means we're talking about having 4 total terms. So what we want to do is identify the row that has 4 total terms. Well, that's going to be this row right here that I am highlighting in green. So the 1, 3, 3, and 1 are going to represent the coefficients of the terms in our expansion. So I'm going to just spread these out. So I'm going to go down here. Okay, we have a little more room. We're going to have a 1 for my first term. And notice I have x for my first term in the binomial. We said earlier that's going to start with a power of whatever n is, so that's 3. And my b value is 2. That is going to start at 0. Okay, so that's going to be my first term. Plus, Pascal's triangle says the next term is going to have a coefficient of 3. Times, well, now x is going to be raised to the second power. It's going down by 1. And my 2 will be going up by 1. So now that's 2 to the first. We go on to our third term. That's going to have a coefficient of 3. X is going down by 1, so now we're at just x to the first. 2 is going up by 1, so now we're at 2 squared. Plus, and then from there, our last term has a 1 from Pascal's triangle. X is now raised to the 0, and my 2 is now cubed. Okay, that's a 0. Okay, so if we clean this up, what we end up getting is x cubed, since anything to the 0 power is 1. This will give us 6x squared. You always want to clean it up, multiply it through. Our next term, we have a 3 times 2 squared. That's 3 times 4, which is 12x. And our final term, 2 cubed, is 8. So there we have the 4 terms in our expansion. So this right here is equivalent to x plus 2 quantity cubed. Now, what if the power of n is very large? Okay, what if we have something that really it's not reasonable to construct Pascal's triangle beyond 5 or 6, maybe 7 rows? Okay, so what if our power is very large? Okay, Pascal's triangle would get very, very messy very quickly. So we have a shortcut, and it's the n choose r command. Sometimes we use vector notation, and we write it this way. Okay, understand that these are equivalent. Okay, just a different way of expressing it. Now remember that n represents the power of the binomial with n plus 1 total terms. Okay, so we see an n right here. And r, this is going to represent the position number in each row. And it's always going to be 1 less than the term number we want. So, let me get back to this. Suppose we want to talk about the row 1, 3, 3, 1. Okay? So 1, 3, 3, 1. We said the n value was 3 here. Okay, and we have 4 total terms. Well, this 1 is my first term. It's equal to 3 choose 0. My second term is 3 choose 1. This would be 3 choose 2, and then 3 choose 3. Okay, so we have term numbers. This one right here is my first term. Notice I had an R value of 0. This is my second term, had an R value of 1. My third term had an R value of 2. And my fourth term had an R value of 3. Okay, so the R value is always 1 less than the term number that we want. To the next page here. Let's look at some different ways to calculate and choose R. Well, first of all, we can find it in Pascal's triangle. Okay, so if we wanted to find 4 choose 2, the n value is 2, and that's going to the n value is 4, and that means we have 5 total terms. If we have 5 total terms, the row we want is the 1, 4, 6, 4, 1 row. So if I am looking for 4 choose 2, this one right here is 4 choose 0. This would be 4 choose 1. The 6 is the one I'm after. That's 4 choose 2. The other ones would be 4 choose 3 and 4 choose 4. Be careful, 4 choose 2 does not suggest the second term. It's actually the third term, okay, in this row of Pascal's triangle. So that's actually, oops, I wrote it in the wrong area. That's actually one technique, all right. The other technique that you could use, or the next one rather, is to use your calculator. You've seen this before. If you go to math and then over to PRB for probability, you would first want to punch in 4 on your blank screen and then select the NCR button and then follow it up with a 2. If you do that on your blank screen, you're going to get 6 for your answer. Okay, so that's the second way of getting it. A third way is to use your calculator again, but this time if you were to go to y equals and punch in 4 and then select NCR from the same technique we saw up above here, and then enter in x. You put that in y equals into your calculator and then looked in your table of values. Okay, so if you look at your table of values, and if you start your table at 0, okay, so if we started it at 0, 0, 1, 2, 3, 4, what we would see here is that we would have 1, 4, 6, 4, 1. These y values would correspond to the row in Pascal's triangle. This is something you want to make sure you try when you have a graphing calculator in front of you. If you don't have one now, again, you want to make sure you try this at some point. So by x, we're really referring to r, and by y, in this situation, we are really referring to 4 choose r. So if we feed this different r values, what you see in this column for y are the different numbers that you would see in Pascal's triangle. So if we're looking for 4 choose 2, all right, our value is 2, you can see that the answer is 6. All right, so straight from your table of values. Now, unfortunately, you're not always going to be allowed to use a calculator, so sometimes you're going to need to use a given formula. It's called the binomial coefficient. And if we're going to find, let's use our example for choose 2 again, we're going to find this without a calculator. Here is our formula. We see some factorials in there. So n is 4 and r would be 2 in this example. So our formula says to do 4 factorial divided by 2 factorial times 4 minus 2 factorial. So recall that a factorial is where you're just going to multiply the integers down to 1, starting with that number. Then we'd have a 2 times 1, and then right here we'd have 2 factorial, which is another 2 times 1. When we clean this up, 2 times 2 is 4. That'll cancel out with that 4. They'll divide each other out. Notice what's left is just 6. Okay? Alright, finally, we have the binomial theorem. This is another formula given to you in your formula packet. And it's another way of expanding out a binomial. It's an alternative to using Pascal's triangle. So it's giving us the expansion. It's telling us in this a plus b raised to the n, the first term is always going to be a to the n. If we jump over here, the last term is b to the n. The second term, okay, this n1 written as a vector is really n choose 1. Okay, and what's happening here is, notice they're showing you that the powers of your first term are going down by 1. Over here is your general formula. This is what you're going to do each time. Okay, so that's equal to n choose r times a to the n minus r times b to the r. So let's suppose we want to use this to expand x plus 3 to the 4th. Well, my first term is going to be x to the 4th. Okay, straight from my formula here, we know it's just going to be x to the 4th. The next term, it's going to be, now my power is 4, so that means that my n value is 4. So n is 4. So if I were to plug in 4 for n, my next term is going to be 4 choose 1 times my x is going to go down by 1, and my other term is going to go up by 1. So we're now going to be at 3 to the 1st. Then we're going to have 4 choose 2 followed by x squared and 3 squared plus my fourth term. We're going to have 4 choose 3 times an x to the 1st and a 3 cubed plus, and now my last term, according to my formula, it's just going to be b to the n. We don't have to fill in the NCR part. It's just going to give you 1. And again, think about Pascal's triangle, how it's just a 1 on the end there. So that's just going to be b to the n, so that would be 3 to the 4th. Okay, so from there, we want to clean it up. So we're going to have x to the 4th plus, now 4 choose 1. If we take a look at that, again, you can use any of the techniques from up above. Okay, 4 choose 1, 4 choose 2. They all came from, if we look up here again, this row of Pascal's triangle, where we had 5 total terms. Okay, oops. So let's go back down here. So this is going to give me 4. I'll just go ahead and clean it up here. We're going to have 4 times 3, which will give me 12x cubed, plus, we said earlier that 4 choose 2 would be 6. 6 times this would be 9. That's 54x squared. Plus, over here, from up above, we know we're going to have a 4 times 3 cubed, so that is 27 times 4. So that's going to give us 108 times x plus 3 to the 4th, which is 81. So this would be our expansion here. Now the good news is most of the time you're not going to have to expand out an entire binomial. Usually you're going to be asked to find a specific term. So suppose you're asked to find the third term in this expansion that we have. So if it's the third term, understand that the R value is 2. So we're going to start off by first identifying that n is 7. So we have 7, choose 2. Don't make the classic rookie mistake of writing 7, choose 3. If we want the third term, remember, think about Pascal's triangle. All right, think about how if we were to look at the total number of terms, we'd have 8 total terms in this expansion. The third term would have an R value of 0. Remember, the first term has an R value of 0. So 7 choose 2 times, we would have 5 raised to the, now what I'm looking at here is this portion of the binomial theorem. Okay, so I'm going to use the n minus r piece, which is 7 minus 2. And then I'm going to be careful here and make sure I put this negative 2x term in parentheses. That's going to be raised to the power of r, according to my formula up above. So that would be squared. So using one of the techniques from up above, if I were to do 7 choose 2, that's 21. 21. This is 5 to the 5th. This would give me positive 4x squared. If I clean this up, we get a very large number. That's to be expected when you have a high power for n. So this right here would equal our third term.